Welcome to the UGC lecture series on lasers on Swayam platform. In this particular lecture, I am going to tell you how any laser works. The essential aspects of laser we will see now. It is bit theoretical. You should have known some basic physics to understand whatever I am going to say. However, I will make it extremely simple and start from the basics. In the earlier lecture, we have seen how the conventional ordinary light is different from the laser light. In the conventional light, the ordinary tube light or sunlight or in the lamp, the atoms and molecules are in thermal equilibrium. Now, what do you mean by thermal equilibrium, which is very important you should know. Thermal equilibrium simply says that the whole world is very lazy. If you put in the proper mathematical forms as given by Boltzmann, Maxwell, you will see it is applicable to the atoms and molecule also. What do you mean by this? Give an example. Suppose we are going to the railway station and we are waiting there and the train is cancelled. They say the train will come after 6 hours late, and there are, let us say, 200 people waiting for the train. Then what will we do? Then most of them will be getting angry, everything is okay. Then after some time, most of them will fall into sleep or sit down or read something. How many of you do you think will be actively doing something, writing or reading a book or anything? Only very few people. That is what is meant by thermal equilibrium. It says that most of the people would like to go to the lowest energy state, which is sleeping state. Only 20% of the people will be sitting or walking around. Only 5% of the people, or at least maximum 2% of the people, would be very actively writing something or reading something or chatting with something, with somebody else. That means active people are far less than the lazy people. Same thing we are going to say. You know, we have hundreds and thousands of atoms. Even in 1 milligram of water, you have hundreds and thousands of molecules, water molecules. If you put them in terms of the energy levels, you will see there are certain energy levels. For simplification, we say E1, E2, E3 like that. Then the picture will show you under ordinary condition, in thermal equilibrium condition, there are very few number of atoms or molecules in higher energy level. This is what you mean by thermal equilibrium condition. This is given by this equation, N2 over N1 is equal to exponential minus E2 minus E1 divided by KBT. T is the temperature in Kelvin, K is a Boltzmann constant, E1 is the energy level, E2 is another higher energy level. That is all you need to know at the point of time. Now, this particular figure represents there will be very few atoms or molecule at a higher energy level. In the case of, for example, in the case of radiation of 500 nanometer, if you put all the numbers, energy, everything in terms of this one, N2 over N1, the number of atoms or molecule in higher energy level than in the lower energy level is 2 into 10 power minus 42 at room temperature, which is extremely small. An assembly of atoms or molecule or human people obeying the above distribution is called thermal equilibrium condition. Next one, suppose we want to put many number of atoms at a higher energy level, you have to give an excitation, you have to supply energy. Only when you supply energy, molecules or atoms will go to the higher energy level. Suppose you are able to give only a very small energy, then you will be able to put only very small number of atoms or molecules at a higher energy level. After some time, they will not stay there, because when you put something at a higher energy level, for example, when I am very angry, I cannot be angry for days, I will be angry for short time, for 5 minutes or 10 minutes, then I will come down, cool down. In a similar fashion, atoms and molecules will come down from higher energy level to lower energy level, and that during this process they will emit light. The light that is emitted during this kind of process is called as a spontaneous emission. Now, look at this one. In this diagram, I have shown you 3. In the first case, there is a lower energy level is E1, upper energy level is E2. Then, if I give some energy, atom at E1 absorbs the photon, goes to E2. This is called stimulated absorption. On the other hand, we go to the next stage. As I told you, the excited atoms in E2 cannot stay there for a long time, and then it will produce emission. This emission is at random. One atom will produce light at this time, another atom will produce light at some other time. There is a time lapse between the 2 atoms. Because of this one, there is a time lapse between 2 photons, or in other words, there is a phase difference between 2 photons. Not only that, that is the first step. Not only that, these photons are emitted at random at different direction. Third one, these photons will have a different wavelength also. All these put together are the characteristic properties of spontaneous emission. On the other hand, to get the laser, you must have a stimulated emission. Stimulated emission means these atoms must be compelled, forced to emit the light at certain time, at certain frequency, at certain direction. There will be a complete control on the emission of excited atoms. This can be done by sending a photon and making this photon play tunes for these excited atoms. That means, the photon that we send in is a leader. It is like a general who trains the soldiers. The general takes them for a walk in the morning, running in the morning, and jumping in the morning. It keeps on training and training and training over years, and eventually those people who had been recruited will come out as trained soldiers. That is exactly what you call something similar to stimulated emission. In the stimulated emission process, you can see, because of the compulsion, one photon produces one more photon. Now, there are, what came in is one photon, what came out is a 2 photon, but these 2 photons both are in the same direction, same frequency, and they all started at the same time. This is the property of stimulated emission. Because of this one, the 2 photons which are coming out under this specialized condition, carefully prepared condition, is the coherent photon, and that is a laser. That specialized, carefully prepared condition is called the population inversion. What is the population inversion? Immediately you can see in the diagram. In the third diagram, you see the number of atoms in the excited state is more than the number of atoms in the lower energy state. In the previous case, in the case of spontaneous emission, the number of atoms in the lower energies is much greater than the number of atoms kicked up to the exit level. That was a normal thermal equilibrium condition. That is the way most of the people behave. Most of the people are lazy, most of the atoms are lazy, most of the molecules are lazy. The second one, to do the laser process, you must specially prepare the atoms and molecule, or another example, you must specially prepare the people in a certain fashion. Coming to the example of army or trained people, what do we do? All the people who are in the army, they are all not aliens, they were not coming from Russia or America, they were all Indians, they were all people like you and me. They were recruited and trained over and over with the benefit. They say, if you join army or navy, you will get so much benefit. Because of the benefit, and also because of they have the strong nationalistic feeling to save the country, to be the protector of the country. They have the honor. Because of the honor, because of the material benefit, they have been stimulated, they have been forced to undergo all the training, and they become first class soldiers, and that is the example for stimulated emission that comes because of population inversion. Now, let us see some basic equations related to this process. That is, already I have introduced only 3 concepts: stimulated absorption, spontaneous emission and stimulated emission. These are the 3 processes which take place when radiation or photons interact with the assembly of atoms and molecules. So, you can imagine you take a number of atoms in a closed enclosure, yes, some kind of container. You have number of atoms. Take for example, you have just 1 gram of hydrogen gas in a container, that is all you need to know. Then in 1 gram there are already millions and millions of hydrogen atoms, you must remember. If I shine light upon it, then the light will stimulate, make the atoms absorb the photons, go to the excited state. This is called stimulated absorption. Second one, those which are excited to the higher energy level will produce light all by themselves. This is called spontaneous emission. The third process, under specialized condition where more number of atoms are in higher energy level than in the lower energy level, the light that is sent in will gain in strength, will get amplified because of stimulated emission. Now, all the 3 we have already seen. Now, let us go to see the equation. Now, the stimulated emission rate should be proportional to, which is given by this equation, dN2 over dt. dN2 over dt means the rate change in the population of energy level N2, that is the meaning of this one. The minus sign always indicates the number of atoms coming down, they are not increasing, they are coming down. This is proportional to rho, which is called the energy density of the radiation which is stimulating it. That is the first equation. Second equation, that one word is missing, that is called spontaneous emission rate. The stimulated emission rate is proportional to the radiation density, and also it is proportional to the number of atoms which are already in the excited state. So, all put together I can now say the stimulated emission rate is equal to B21 rho N2, where the letter B21 represents Einstein's stimulated emission coefficient. For the first time we are bringing the word Einstein, because it was he who said that stimulated emission is possible. Before that there was no such an idea. There is an event that is possible of stimulating the atoms to produce light. He was the first one to say this one. So, we say B21 represents Einstein coefficient for stimulated emission. That rho is the photon density or energy density. N2 represents number of atoms in the higher energy level. This is for stimulated emission rate. In a similar fashion, you can write down another equation which is called the stimulated absorption rate. This is minus d1 by dt, because the absorption takes place from a lower energy level N1 to higher energy level N1 to N2. Now, this is equal to B12, not B21, B12 rho N1. Here again, rho represents the energy density of the photons, energy density of the radiation field, or in fact simply the number of photons which are inducing this effect. Then N1 represents the population in energy level N1. Now, we have got two coefficients B12 and B21. B12 represents stimulated absorption rate, Einstein's coefficient of stimulated absorption from 1 to energy level 1 to 2, B12. B21 represents Einstein's coefficient for stimulated emission, that is B21. These are essentially an intrinsic parameter which depends upon the energy density, number of atoms, and also property of the particular atoms and molecule. A represents ordinary spontaneous emission coefficient. Now, let us go to the next step. For many atoms and molecules, B12 is equal to B21. So, let us put B12 is equal to B21. For simplicity, we will call it as a B. Now, put this equation together, you can immediately see to have stimulated emission greater than stimulated absorption. See, when you have stimulated emission greater than the stimulated absorption, then only you will see the photons coming out. It is something like taking the people for army. If you take 10,000 recruits from Tamil Nadu, for example, and they give the training, you must have 10,000. Out of that, most of them should come out, many number of them, at least 8,000 should become soldiers, only 2,000 should not, they fail any kind of training. Then only you will have more and more soldiers coming into, joining into the Indian army. B rho N2 should be greater than B rho N1, because the first one represents the total photons which are coming out due to stimulated emission. The second one, B rho N1, represents the total photons which are lost because of stimulated absorption. Now, from this equation immediately you can see, since B is same, rho is same, automatically it implies N2 should be greater than N1, that is, number of atoms should be greater in the higher energy level than in the lower energy level. This is what is called inescapable, essential, prerequisite for coherent amplification. For any kind of strong country, they must have a regular batch of people coming out as soldiers every day, every year. They recruit, give training, and they become soldiers. They recruit, give training, they become soldiers. Some of them will disappear, some of them will die in the war, but they will keep on recruiting more and more training. So, this will be a dynamic equilibrium. In a similar fashion, those who are trained soldiers are similar to our laser radiation, because trained soldiers are coherent, they are very orderly, very disciplined. To have a disciplined, orderly, capable soldiers, we must have essential, that is the population inversion is an essential process for any kind of coherent amplification of any kind of laser action. Now, we will go through this equation. Consider again another equation. In this equation, we have said B rho n 1 minus, I am just skipping few of them, B rho n 1 minus n 2 is equal to A n 2 when you equate this one. Then A spontaneous emission rate, Einstein's spontaneous emission coefficient, divided by B rho. A represents spontaneous emission rate, B rho represents stimulated emission rate. Then this comes as n 1 divided by n 2 minus 1. You can simplify this equation when you go through. Then you can see the next step, n 1 minus n 2 is exponential delta E by kBT, which you have already seen. This is the very famous equation of Maxwell-Boltzmann. So, A over B rho becomes automatically exponential delta E divided by kT minus 1. Follow this one, then you will see B rho by A stimulated emission rate divided by spontaneous emission rate. This is exponential delta E over kT minus 1 over minus 1. That means the whole thing is 1 over exponential delta E divided by kT minus 1. The whole bracket is 1 over something, that is why I put minus 1 on the top of it. Now, from this we can get an important information. Let us assume that we are dealing with a radiation of lambda 500 nanometer. 500 nanometer is a green color with which we are all very familiar. Now, the wavelength is 500 nanometer, means the frequency will be 6 into 10 power minus 14 hertz. Imagine such a radiation is contained in a small cube, small container, and kept at the room temperature of 300 Kelvin. Now, substitute all those one, you will see under workable temperature stimulated emission almost impossible. It can be seen that for 10 power, for 500 nanometer under ordinary condition, it is very difficult to get laser action. On the other hand, if the wavelength is about 60 micrometer, under this condition you can work out and you will see B rho is approximately equal to A, which means that is I can go back to this equation, you must substitute all these in this equation, then you will see at 60 micrometer stimulated emission rate is something approximately equal to spontaneous emission rate, or in other words, for a wavelength range of 60 micrometer, most of the radiations are stimulated emission. The spontaneous emission rate is equal to stimulated emission rate, which means it is much easier to get laser action. 60 micrometer is somewhere in the microwave region. That was the reason why laser action was much easier to observe in microwave region, that was called MASER, microwave amplified stimulated emission of radiation. In fact, MASER was achieved much earlier than the laser. Under that condition, under ordinary condition, you would get mostly in the microwave region, it is much easier to get stimulated emission. On the other hand, when you come to 500 nanometer, which is the visible region, it is very difficult unless you do something special. We are going to do a special condition under which we will be able to get laser action. Now, let me sum up. in the next lecture you will see what is the special condition. What is important so far is, when you take an assembly of atoms, plenty of atoms, say 1 gram of hydrogen in a container of 1 meter, just imagine, then you have millions and millions of hydrogen atoms. Most of the hydrogen atoms are under the lowest energy level. There are very few atoms at a higher energy level. They always produce spontaneous emission if they are excited at all, otherwise they will not do anything. Now, we have seen earlier, to get a laser action, to get a coherent light, you must have an extraordinary condition of population inversion. Under population inversion, whatever radiation that comes out is coherent. Now, look at this one. This kind of population inversion and stimulated emission, coherent amplification, all of them are much easier to sum up, get it at the microwave, but in a laser you need a special condition. What is that special condition? We will see in next lecture. Thank you very much.